At this point, we should recognize this problem as a simple nonlinear problem, something that we can solve easily with feature cross products. But what happens if we get a slightly more complicated problem? Maybe something that looks like this. At some level, we've got maybe a set of spirals interacting with each other. Now, we could probably sit around and do some math and think of the right feature cross products to add, but it's easy to think that our data sets might be more and more complicated. And eventually, we would like some way for our models to learn the nonlinearities themselves without us having to specify them manually. This is the promise of deep neural nets that do an especially good job at complex data, including image data, audio data, and video data. We'll learn more about neural nets in this section. So we'd like to have models that learn the nonlinearities themselves without us having to specify them manually. How are we going to do that? Well, we probably need a model with some additional structure to it. Let's take a look at our linear model, where we have a number of inputs, each with a weight that's combined linearly to produce an output. Well, if we want to get a nonlinearity in there, maybe we need to have an additional layer in there. So now we can add those guys up in a nice linear combination into a second layer. That second layer gets linear combined, and we haven't yet achieved any nonlinearity because a linear combination of linear functions is still linear. Okay, well, that's not good enough. So clearly what we need is a second layer, right? So we put a second layer in there, and we're still linear, because even if we add as many layers as we want, any linear combination of linear functions is still going to be linear. Okay, we need to do something else. And that something else is we need to stick in a nonlinearity. That nonlinearity can go at the output of any of our little hidden nodes in there. One common nonlinearity that we use is called ReLU. And this takes a linear function and chops it off at 0. So if you're above 0, you're a linear function. If your function returns a value below 0, we cap that at 0. Simplest possible nonlinear function, and this allows us to create nonlinear models. Now, we could use any nonlinearity in here. A lot of folks also use sigmoid or tanh, but it turns out that ReLU gives state-of-the-art results for a wide number of problems, and it's very simple. Once we have this, we can stack these layers up, and we can create arbitrarily complicated neural networks. Now, when we train these neural nets, obviously we're in a non-convex optimization, so initialization may matter. The method that we use for training these is a variant of gradient descent called backpropagation. And backpropagation essentially allows us to do gradient descent in this non-convex optimization in a reasonably efficient manner.